At the end of the lesson, you are expected to identify regularized least squares. Use regularized least squares to penalize a model over complexity, and appreciate the significance of regularized least squares in machine learning. Let's remember that the more parameters we add to our model, the more complex our model becomes. So that's actually very basic in modeling, and we had that in our previous lesson. So one of the problems is having higher absolute values. Again, we are considering absolute values because positive and negative values cancel each other. Defining our model complexity, we have this expression. So we have the summation of W squared, or if we would like to use a vector form, then we have this W transpose W. So before we continue, hit that subscribe button to enjoy more our deep learning, mastering machine learning, and natural language processing courses. Click the notification bell to receive more updates. Okay, so let's continue. If we are going to examine our expression, we can see that we are averaging the squared loss in this case. So we have here, right? So remember this, we are just having this one, and then after that we can take the average. So let's remember that. Okay, anyway, before going to that, this kind of process, if we're going to do this, then a certain problem is unavoidable. And this problem in keeping this kind of way is it does not keep the value of the loss low. So let's remember that our goal is to make it really very low in as much as possible. So what are we going to do then? What's the best way? Still remember the average we had in our cross-validation? So I'm going to put the link of our previous lesson in the description below. So we are still going to use it. So to avoid overcomplexity, we are going to sum up the previous loss during the cross-validation and a term that penalizes overcomplexity. Let me write here. Okay, again, we are going to sum up. And how to do that? How to express this statement into a mathematical form so that we would not be able to forget this concept very easily. So we have this. Okay, the loss, our regularized loss, is equal to the loss. This is the loss that we had before here, and then we have plus, then we have the eigenvalue W T W, this one. Okay, so what does the eigenvalue here stand for? What is its main function? Okay, so this eigenvalue controls this one. This eigenvalue controls the trade-off between the loss and the overcomplexity of the model as shown by WT or W transpose W. Again, let me repeat this, that this one penalizes overcomplexity of the model. Okay, so again, overcomplexity has something to do with having a lot of parameters. Okay, so having all this said, our original squared loss is now like this one. Okay, so we have L, or regularized loss, is equal to 1 over n W transpose X W minus 2 over n W transpose X transpose T. Or in some cases this can be Y. It depends on which one you prefer to use. Then we have plus 1 over n T transpose T plus eigenvalue W transpose and W. Okay, so if we are going to take the partial derivatives of, or the partial derivatives with respect to W1, then we have this one. So the partial derivative of the loss with respect to the partial derivative of w is equal to 2 over n x transpose xw minus 2 over n x transpose t plus 2 eigenvalue w. So if we are going to set this expression to 0 and do all the steps, we can have this. We have this one, w or w hat is equal to the inverse of x transpose x plus n, eigenvalue inverse, then x transpose t. So I would like to leave you all the necessary steps for us to arrive at this point from this point. You can just do the process and prove for yourself that this one and this are actually the end-to-end process. Okay, so now what if we are going to set the eigenvalue to 0? Okay, eigenvalue is equal to 0. What would be the effect? So if this is the case, we go back to our original solution. And maybe you would like to ask me, why is that so? Why is it that we go back to our original solution, which is this one? If we are going to use 0 as the value of our eigenvalue, okay? This means that regularization does not have any impact in our data points. Why? Because again, 0 has no value, right? Okay, let me use another pen for me to do some writings here for you to be able to understand. Okay, why? Because any number that is multiplied to 0 is also 0. That means for this kind, it becomes 0. And what remains here is this, which is this. We would go back to this one, right? And this one, this part of our equation which penalizes over complexity would now be 0. So that means again we go back to the very basic. So it's as if we have done nothing. Okay, and again, in short, that means the eigenvalue that we set with a 0 has no impact in our data points. So if we would like to see better changes as to the fitness of our model, what we should do is that we're going to increase the value of the eigenvalue. So we have to be very cautious in choosing the value of our eigenvalue, because this may result to overfitting or underfitting. Okay, so there are some considerations that we have to take note of. So we have here the first one. So having two small eigenvalue, for example 0, or even if we are going to have 0.00001, which is almost 0, this can make our model too complex. Okay, let me write here, too complex. What if we're going to have too large eigenvalue? What would be the effect then to our data points or to our model? So having too large eigenvalue may not be able to capture useful trends in our data. So this may not be able to capture the trends. Okay, so these are the two problems we're going to meet. Now, what we're going to do is that we're going to choose something that is in between. One that is not too small, not too large, not large, just in between. How are we going to find that? So at this very moment, the best question to ask is, how are we going to properly identify the best eigenvalue? Is there a proper way? So, well, we are very fortunate because we can use a validation technique to do this. So our previous lesson about cross-validation teaches us how to correctly identify the best eigenvalue. So let me write here, cross-validation. So in our previous lesson, we talked about the k-fold cross-validation. So that method is the most effective way for us to be able to identify the best eigenvalue to be used. Okay, so using this cross-validation, we would be able to identify the best predictive performance. So I'm going to give the link in the description below. What is this for? Why do we have to study this? We use regularized least squares for two main reasons. First is that when we introduce or when we have a lot of variables, it becomes impossible to fit the ordinary least squares. So with this, regularized least squares introduce more constraints. And then we regularized least squares when the generalization of the learned model is very poor. So this is caused by having more number of variables than the number of observations. Regularized least squares is used to improve generalization of the model. After all being said and done, let's try this. How do we use regularized least squares? Why do we use regularized least squares? Please leave your answers in the comment below so that we would be able to have a very rich interaction of ideas and we can learn from each other. Do you want to know more about this course? Just click the card on your right screen. You can enjoy our deep learning, mastering machine learning algorithm, and natural language processing courses. Learn and upskill for free.